This is the last video in our gas laws unit. It's going to focus on gas math, specifically converting between moles and grams and liters of a given substance and being able to do that with chemical reactions as well. As we've seen before, 1 mole is equal to Avogadro's number, and that's going to be applied to atoms, molecules, and formula units. We've also seen before what a mole is equal to, that it's equal to its molar mass in grams, and that we've already talked about Avogadro's number, but our new value is going to be the 22.4, and that's going to be applicable for gases that are at standard temperature and pressure. So just like with our pressure conversions, how we could go between atmospheres and millimeters of mercury and kPa and use any of those three to be set equal to one another, we can use any of these particular quantities, moles, grams, and liters, and set those equivalent to each other, as long as we use the proper quantity when converting between those units. So our first example is going to be a mole conversion. We're going to start in 45 liters of hydrogen gas at STP, and we're going to convert that to moles. So we start with what we're given, the 45 liters. We want to cancel out our liters, so they go in the denominator. The moles go up top. We know that liters should always get 22.4, and moles should always get 1. That's what the relationship is between moles and liters. Our liters will cancel out, and our numerator will have 45.0 times 1, and we'll divide that by 22.4. Both numbers have 3 sig figs, so when we calculate our answer, we want to round it to 3 sig figs, and we get that that should be 2.01 moles. Sorry, I went a little too fast. Our next example is going to use grams and go to liters. So we're starting with 24 grams of CO2 at STP. When we convert from grams to liters, grams needs to go in our denominator and liters needs to go in our numerator. Liters still gets 22.4, but grams has to get molar mass. We have to use our periodic tables to get that, so we go and find carbon and oxygen on our periodic table. Carbon is 12.01 grams. Oxygen is 16. We need to double it because there's 2. Again, those are the atomic masses for carbon and oxygen from your periodic table. And then when I do the math for that, I get 44.01 grams is the equivalent of 1 mole of CO2. That is its molar mass. Molar mass goes in front of grams in our conversion factor, so that 44.01 will go up there in front of the G. 22.4 stays with the liters. The grams cancel out. So we're going to multiply 24 by 22.4 and divide it by 44.01. 24 has 2 sig figs, so when we round our answer, we want it to have 2 sig figs. And its unit will be in liters, so that's going to be 12 liters. Our last conversion is a little bit different because we're going to be finding density. We've done density before, but not with gases at STP. Density, if you remember, is mass over volume. And the only thing we know about STP so far is that when we have 1 mole of a gas at STP, we have the molar volume of that gas, 22.4 liters. We also know that when you have a mole of a gas at STP, or a mole of a gas under any condition, that's going to be equivalent to its molar mass. So since we need a ratio of mass to volume with the same number of particles, we can set the molar mass in grams as our mass and divide it by the molar volume, 22.4 liters. This will allow you to find the density of any gas at STP by finding its molar mass and dividing it by that 22.4 liters. We need to remember that fluorine is a diatomic element, so when we find the mass of fluorine, we need to double 19 and get 38 for that because of the 2 fluorines that are always present when you have a molecule of fluorine. Divide that by the 22.4 liters. We have 4 sig figs in our molar mass, 3 in the 22.4, so we're going to have 3 in our answer, which will be 1.70. We'll round it up from 1.69, and both units are included because it's a ratio of mass per volume. So 1.70 grams per liters. The second half of this video is going to focus on stoichiometry. Remember that the biggest differences between just mole conversions and stoichiometry is the use of a balanced equation, specifically using the coefficients to represent the ratios that exist molar-wise between elements and compounds in that specific chemical reaction. And so that when we do our conversions, we have to include those coefficients to help us see how the different substances relate to one another. The reaction is acting as our recipe. So in this particular example, we have nitrogen and oxygen making N2O5. This reaction takes place at STP. How many liters of oxygen gas are required to produce 15 liters of dinitrogen pentoxide? So we start with what we're given, the 15 liters of N2O5. The liters of N2O5, it's really important this time to include your chemical formula since you're changing formulas as you move from your starting point to your final part of the problem. We're going from liters of N2O5 to liters of O2. We get O2 from our balanced equation. Oxygen, remember, is a diatomic when it is by itself. As we saw in our previous conversions, liter always gets 22.4, so that will go both in the numerator and denominator of our conversion factor. And then we need coefficients. Oxygen, if we look up here, has a 5, while N2O5 has a 2. And so that's why we see the 2 going in front of N2O5 and the 5 going in front of O2. The liters of N2O5 cancel out, and if you look closely you can see that 22.4 also cancels out. If you don't see that, it will still work. You just need to make sure you follow your help your calculator out with multiplying both numbers in the denominator inside of one set of parentheses. 15 times 5 gets divided by 2. You have 2 sig figs because of the 15. So we need 38 liters of oxygen, and if I remember correctly, that rounded from 37.5. I'm going to do 2 more examples. This one's not going to be as simple because we're not just going to go from liters to liters. We're asked how many liters of oxygen are produced if 2.58 moles of aluminum oxide are completely decomposed. So we start with what we're given, the 2.58 moles of Al2O3. Moles of Al2O3 need to be canceled out, so they go in the denominator. Again, oxygen's a diatomic. You can see that in the balanced equation. So liters of oxygen go in the numerator. Moles will always by default get 1, and liters will always get 22.4. And then according to our balanced equation, aluminum oxide will relate to oxygen in a 2 to 3 ratio. So 2 goes in front of aluminum oxide, and 3 goes in front of oxygen. So that accounts for the stoichiometric relationships. We can cancel out our moles of aluminum oxide, and at this point we will multiply the 3 numbers in the numerator, 2.58 times 3 times 22.4, and divide everything by 2. And that will give me 3 sig figs because of the 2.58 moles, and the final answer will be 86.7 liters of oxygen. Our final question is going to go from grams to liters, so we're going to skip over moles completely, and we can do this too in one step. How many liters of hydrogen are made if 7.52 grams of ammonia is decomposed at STP? So we start with what we're given, the 7.52 grams of ammonia. When we set up our conversion factor, grams of ammonia needs to go in the denominator. Liters of hydrogen needs to go in the numerator. Grams again will get the molar mass of NH3, so I would go and find N and hydrogen on my periodic table, multiply hydrogen by 3 and add it to the mass of nitrogen. That would give me 17.04 grams. Liters gets 22.4, and according to my balanced equation, it is a 2 to 3 ratio between ammonia and hydrogen, so the grams of ammonia cancel out. I need 3 sig figs in my answer because of the 7.52. So that gets multiplied by 3 and 22.4, and then divided by the product of 2 times 17.04. Watch out for your parentheses again, and when you do the math for that, you should get 14.8 liters of hydrogen gas. So this is the end of the last video in our gas law unit, and you should be able to do the gases and mole worksheet as well as the gases and stoichiometry worksheet at this time.